Greetings. In this video, we will solve a second order differential equation. It will involve a double derivative of y, where we are solving. The goal of this video is to solve for y of x. So what is this function, single variable with respect to x? Then we subtract from it y itself, and we're looking for it equal to 0. And now we're looking for y. What is y in this equation? Well, when I write y double prime, what I really mean is double derivative of y of x. And y, I mean y of x. But for simplicity, I wrote it that way. We could just leave y double prime and y the way they were. And with these kinds of equations, we always anticipate the result to be in the form y equals e to rt, where this is an exponential function base e, approximately 2.7 and so on, with its decimal development. And then we have independent variable x in the exponential function. So we have this r multiplying the independent variable x inside the exponent, and we want to find the value of r. X is obvious, e to the x is obvious, but we want to find how many x's are in the exponent. So how do we do that? Well, if we anticipate y to equal to e to rx, then this thing, if we double derivative it, well, what is the double derivative of y? So we can plug it into this equation, all of that. Well, that is the derivative of the first derivative, which is going to be once more as follows. So this is the y double prime. I can put it here. So I have r squared e to rx. And then minus y of x. Y of x, well, y of x, or however you want to call it, is e to rx. So e to rx right here. And the equation still equals to 0. So this is the point here. And now we can divide both sides by e to rx. And this is the point of this whole method, where we will just find the value of r, so that we can then replug it back here into this expectation. So r squared minus 1 equals 0. Only thing I did is just divided e to rx on both sides. Now, r squared equals 1, r equals plus minus 1. So we have these two possible concrete solutions. y1 equals e to x, and y2 equals e to the minus x. But the thing is, with differential equations, such ones, when we have more solutions, we take all the possible, it's a complete family of solutions. We take all linear combination of the solutions we got. That means that y of x would not only equal to either this or this, but it will equal to all linear combinations. That means it will equal to any c1 times e to the first variant of it, plus c2 times the second solution. And yes, what is meant by this is c1, c2 are some scalars belonging to reals. And so you can plug any normal numbers for c1, c2. So any linear combination of these two solutions, e to x and e to minus x, will suffice for this solution. And just to check it, just to check that what we calculated is right, we can quickly put it in, and we can put in the general thing. So our general solution here was this solution, and I can put it in this equation. What I did thereby is this actually doesn't change. That's very practical with the exponential functions. Then we have minus c2 e to the minus x, but we have to take the derivative once again, and then minus the y of x. Well, again, I plug it there, but that doesn't change at all, and there's no more derivation required after that. And it all should equal to 0. Does it satisfy that? Well, it does, because this is derivative once more. c1 e to x again stays the same, and this minus here makes this plus back. So we get this. And then we subtract basically the same thing. So the point here is that, by the way, this was a small mistake. Here should be plus. And because of that reason, we see these two things cancel with each other, and they do equal 0. So it is satisfied, and our solution is verified.